All right, so good morning or good afternoon, depending on where you're joining us from, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. If you're joining us for the first time, we're all about bringing conservation, adventure, and science into classrooms around the world. Now, January has all been about STEM careers. We featured a whole gamut, a whole slew of incredible people from across the globe sharing their stories of how they got into some really top-notch best careers in the world sort of deal. Today is particularly exciting. We have 4 programs today. So we started out the day in Cameroon in the jungles of the coast. We went to Antarctica to explore the seafloor. And now we are literally blasting off into space with Dr. Sarah Milkovich. So she is a planetary geologist and NASA systems engineer at the Jet Propulsion Laboratory. So this is one of the elite research facilities in the world that's been responsible for understanding and exploring other worlds. And Sarah gets to work to understand those worlds and build the things that go and actually explore them. So if there's a cooler job than that, I can't think of what it is. I'm so excited to have you here with us today, Dr. Milkovich, and take us away.
Thank you very much. Yes, so I am a planetary geologist and what's called a science systems engineer. And what all of that means is that I am basically a scientist by training, but I work very closely with engineers because engineers and scientists bring different perspectives to solving problems. So to an engineer, if you want to land on Mars, you need to find a really safe place to land. So this is a safe landing site. It's very flat. It's pretty smooth. There's lots of little pointy rocks, but they're not too pointy. There's not too many of them. They're pretty small. This is actually a picture of the landing site of the Spirit rover on Mars. Now, the thing is that if you are a geologist like myself, where you want to go on Mars, where you want to send your rover, is to interesting rocks. And the most interesting rocks tend to be the pointy rocks. So this is a picture of Bryce Canyon in Utah. This is an amazing place where water and wind has shaped the surface, and we can figure out all these amazing things about the history of this location, because every layer of rock is like a page in a history book, and it records what the environment was like in this area back when that layer of rock was being formed. But the thing is, if I went into the landing engineers, the entry, descent, and landing engineers offices, and I said, this is where we want to land our rover, they would just laugh me out of the room. So my job is to bring the perspective of science over to the engineers and then translate the engineering constraints, the real world constraints, back over to the scientists to work to get the best possible science, the science data within our engineering constraints from our robots as they go out and explore the solar system. So I'm going to give you a very brief rundown on kind of my career path on how I ended up in this sort of unique niche of a job. And then I'm going to talk to you about the project that I'm working on right now. So when I was growing up, I loved rocks. I visited Bryce Canyon when I was young, but I grew up in upstate New York, where the rocks looked more like this. This is some of the rocks and a waterfall from my hometown of Ithaca, New York. And you can see that the rocks are very different. And I became fascinated by this idea that the world around us and the rocks that we walk on and we see on like road cuts as we're driving along, that they can tell us the history of an area. They are like a puzzle and a mystery in a different language where half of it is missing. And so it's a big puzzle to solve. And I found that really fascinating. I was also a gigantic fan of stargazing and astronomy. And then I discovered you could put these two things together and in planetary geology. And in high school, I actually did a summer internship with the camera team for a spacecraft that was launching called the Near Earth Asteroid Rendezvous. So there's me in high school with 2 of the women that I worked with. And that's a picture I took. They took me to see the launch of the spacecraft, and that's a picture I took. And up in the corner is a picture of an asteroid that it flew past on its way to going in orbit around another asteroid. And once I had that experience of the team camaraderie and the idea of going out and exploring the solar system using robots, I was hooked, and I knew that this is what I wanted to do in some way or another. I moved out to California to go to college, where I actually majored in planetary science, which is pretty unusual. There's not a lot of places that you can do that at. But I also was very active in the music program. I played trombone, and also student government. When I finished up there, I moved back out to the East Coast to Brown University, where I got my master's and PhD in planetary geology. And doing all this, I was studying these ice deposits on Mars. There's these, just like how on Earth we have ice at the poles, on Mars we have water ice at the poles as well. And when we look at them, they have these dusty layers in them. So this is an ice record of the changing climate of Mars in the last 5 to 10 million years, just like how on Earth we can study ice cores to look at the climate record here. That's what we were trying to do from orbit on Mars. And that was really interesting, but I really decided that I wanted to get more involved with the spacecraft themselves rather than focusing on the research from the data that they send back. I joined JPL in 2005, and we're all working, most of us are working remotely from home right now, but here's a picture of some of the women at JPL taken in 2018, and I'm somewhere in the front in one of the people in a red shirt. So it's a place, there's about 6,000 to 7,000 people who work there, and we work on all different kinds of aspects of exploring the solar system with robotic spacecraft. And that's many different kinds of scientists, oceanographers, people who study atmospheres, physicists, astrophysics, geophysics, planetary surfaces, planetary evolution. There's also all different kinds of engineers, from mechanical engineers, electrical engineers, computer engineers to write the software that run on our spacecraft. But we also have to have, when you have that many people, you also have to have the types of people who think about finance to make sure that all of this big team is working together and being paid, but we're not going too far over budget on our projects. And you have managers, and we also have artists who work at JPL. They do a lot of the mission art, and they also help make things to explain what we do to the rest of the world. And also they make little installations to help us be inspired as we go around our day as well. So it's a really great place. My first job there was to work on a lander in sort of the Arctic plains of Mars called Mars Phoenix. It landed, and I was in charge of, I did a lot of sending it the codes, the sequence of commands up to the lander to tell this little fork that's on the end of the arm what to do. And we could stick that fork into the ground and measure thermal and electrical properties of the soil. So I was taking what the scientists said, these are the measurements we want to take, and I would turn those into the commands for the instrument that went up to Mars. But Mars Phoenix was a solar-powered mission, and at some point the sun went down in the Arctic of Mars and it died. So I went off to work on Cassini, which was a spacecraft in orbit around Saturn. So there's a picture that Cassini took of Saturn, and one of the things I love about this picture is it's beautiful. It's a work of art in itself, but it also tells you so many things. There's the line that's going sort of diagonally across the center of the image is actually Saturn's rings looked on the edge, but you can see the shadow that the sun is casting being on the surface on the top of Saturn's atmosphere. So you can see how narrow the rings are, but also how broad, how wide the rings are by looking at the pattern of the shadow. And then the little circle there, that is Titan. That is one of, that's the biggest of Saturn's moons. That is a fascinating world in its own right. And I'm not sure if you can see it on the screen, but if you go find this picture on one of the NASA websites, right around, you can see that the shadow of the rings is a little disturbed very close to Titan. And that's because Titan has a very thick atmosphere. So there's so much science that we can learn from this image, even as it's a beautiful thing. So on Cassini, my job was very much about bringing the scientists together to plan chunks of time. What are we going to do with this spacecraft? And I worked on that for a while, but eventually Mars was calling again, and I left and worked for a camera on an orbiter at Mars called Mars Reconnaissance Orbiter. And this is the HiRISE camera. It's a super high resolution camera. It's really one of my favorite cameras in the entire solar system. From about 250 kilometers above the surface, it takes pictures that are very high resolution. We can see boulders that are probably slightly larger than a car. So that size on the surface. It's color. What you're looking at here is a set of sand dunes with bright dust covering them, and then little storms called dust devils have come across and lifted up the bright dust and left the dark sand behind. And there's also some little sand and dust avalanches on the side of the dunes. At some point, working on all of that, I became interested in not just helping the scientists take their data, but how the scientists and the engineers talk to each other, the process by which they talk to each other and figure out what to do with these amazing robots. And I went and I worked on the Curiosity rover for about 6 months before landing and then 3 months after landing, helping make sure that the science team was ready to go and that they were all ready to operate the rover when it landed. And that really gave me a taste for sort of this behind the scenes of science operations. So I currently work on the Perseverance Rover. This is an artist's rendition of it, highlighting all of our amazing science instruments. That's what I work on now. I started in 2013, back when there was a small group of scientists saying, okay, what are we going to do with our next rover? And we started out, basically the whole rover itself was just ideas on pieces of paper, and this is us checking them. This is all different pieces of paper with ideas about the science that we could do taped onto the wall as we prepared our report. And then I've spent many years working to design the operations processes, the software concepts, working with the software designers on what kinds of planning tools we need, working with the people building the actual physical rover on how their choices are going to affect the kinds of science that we can do. And now my job is to make sure the science team is ready to go when we land, which is not that far away. So now I'm going to tell you briefly about this rover I'm super excited about. So welcome to Mars. Here's a picture of Mars. Mars today is a cold desert, and we can't support liquid water at all on the surface of Mars. It's too cold. The atmosphere is too thin. It's very inhospitable. There's high radiation on the surface. It's just not a nice place to when you're thinking about life. However, we've been studying Mars for a long time, and we know from the geology and the chemistry of Mars that ancient Mars, talking about 3.5 to 4 billion years ago, ancient Mars had liquid water on the surface. So it had lakes, it had rivers, it may even have had oceans. What's fascinating about this is that ancient Earth at around the same time was very similar to Mars. The two planets have grown up and evolved in different directions since those very early years. And in that very early time period, that's when life started on Earth. So we think, well, if life began on Earth at around the same time that Earth and Mars were very similar, maybe it could have started on Mars as well. And that's what this rover is all about, looking for signs of ancient life on Mars. So what are we going to go look for? Well, when you think about ancient life, you probably think about fossils. But all of the classic fossils, including things that seem quite simple, like leaves or little fish, those are all less than 650 million years old, and we're talking about billions of years. That time frame, for a huge chunk of time on Earth early on, we only had microbes. So we are looking for evidence in the rocks of microbes, and we're calling them microbial biosignatures. So here's a picture of some microbes, some fossilized microbes on the Earth. These are we've found these that are as old as 3.6 billion years. And they're basically layers and layers of algal mats that build up in these shapes called stromatolites. So that's what we're going to look for. We're going to look for trace remnants of microbes. We're going to look for patterns in the chemistry and the shapes of the rocks. And these are all going to be very subtle patterns, which is a big challenge for us, and part of why we're sending some very complicated instruments. We are also sending a drill to drill samples of rock that seem interesting, place them in tubes, and leave them on the surface of Mars for a future mission to come pick up and bring back to Earth so that we can study them in the laboratories here. And so maybe some of you will someday end up working on studying the rocks that this rover is going to bring back. So we packed up our rover last spring, and so we have the rover. It's got a jetpack backpack to get it onto the surface of Mars, and then it's all packaged up in a nice little box. And what we call the cruise stage is placed on it, and that's what gets us to Mars. We launched July 30th, 2020, and we are currently cruising to Mars. We're almost there. We land 22 days from now. We land February 18th, and we're all very excited and nervous and tired because we're trying to finish up put all the last touches and practice how we're going to operate this thing. So it's quite a busy time for us. We're going to this crater on Mars called Jezero Crater that once upon a time it was filled up with a lake. What you're doing is you're looking at sort of a side view of the crater. So there's a crater wall in front of you. There's a channel that cuts through that, and then there's this fan shape that's coming towards us out of the screen. That is a river delta. So here's a river delta on the Earth. So we know that this ancient crater had a lake in it. It had a river going in. And we know that on Earth, river deltas are habitable environments. All of those splotchy colors on the mud there, those are all different forms of algae and microbes. So we are going to start our adventure on Mars by driving to this delta and exploring it and looking for these subtle patterns in the rocks that could give us information about the possibility of ancient life on Mars. So thank you. That's my whirlwind tour. And you can follow along at this Twitter account and on these websites. And with that, I'd be happy to answer any questions.
Fantastic.
I will stop sharing my screen.
Yeah, nice to come out of screen share. You can have a bit of a conversation with us, but I do encourage all our classrooms tuning in. Check out those links. No one does space education better than NASA. They've got an incredible slew of resources to follow along with missions, keep learning going, and more. And I can't believe you're joining us today, Dr. Milkovich. I completely forgot that February 18th is the landing. I don't know. How do you have the time for this? What are you doing? Jeez. Anyway.
A lot of coffee. A lot of
coffee will help. Well, I'm so glad you could join us. We have, like, it's a ridiculous number of kids. I think we have 500 kids tuning in between our YouTube classes and our live groups. So welcome in across the continent. Where do we have a little from? Alberta, BC, Kansas, Connecticut, New York, Florida, Ontario, and more. Let me know where you're joining from in the chat if you haven't already. I'd love to get a sense for Sarah by the end. But let's dive in with questions, guys. I'm actually going to start with one YouTube question and give our live classes a chance to, solidify their answers here. Mr. Mayot's class wants to know, how long does it take to send a signal to the rover and actually have it register that and actually do that command?
That is one of the great challenges of this kind of exploration. So it depends on where the two planets are in their orbit. So if we're sometimes during the Mars year, it's only about five minutes or so for a signal to get from Earth to Mars. But there's other times when it's like 25 minutes. And sometimes Mars is on the other side of the sun from Earth, and we can't talk to any of our robots there at all because the sun just interferes with our signal. So but I used to, as I said before, I used to work on Cassini, which was out at Saturn, and that took about an hour for a signal to get out there. So you can imagine we're not like operating this with a joystick, or like when you're playing your video games and you're doing like Mario Kart or something and driving around on the screen. We actually build a to-do list for our spacecraft and send up a big chunk of commands at a time. So for Perseverance, it's going to be usually about 1 day's worth of to-do items. And then each day, so when it finishes that, it'll send some data back, and while it's asleep, we think about what are we going to do next and build those commands and send them up. But for something more like Cassini, we built about a month's worth of to-do items because talking to the spacecraft had to be extremely carefully planned out ahead of time.
Very cool answer, and thanks for the question. For our live classes, you don't need to type in the chat. I am going to come to you guys live in a second. I'll go one by one. We're going to start with this else class joining us in Toronto. If you guys want to just demute your microphone and come on in, you're good to go.
Hi. We have quite a few questions, so I'll just pick.
Start with one, and we'll come back if we can for another.
Yeah. Okay. So, one of the questions asked was, what is the coolest thing that you have found on Mars?
Ooh, no pressure.
Oh, that is a hard question to answer because it depends on, every scientist has their own little perspective, right? And so each person will be like, this is the most exciting thing. And then then they argue. But I think one of the things I think is extremely exciting about the science that we're going to do with this rover is that all of our previous missions have showed us that we have all the right conditions on ancient Mars to support life. Yeah. But we haven't really had the right instruments to do the detailed chemistry assessment that I was mentioning. One thing that I think is fascinating is that ancient Mars, the crust is all still there. On Earth, most of that ancient crust has gone away because of plate tectonics, and so subduction zones, volcanoes, and everything. Our crust is very young, so it might actually be that we have a better record of that time period on Mars than we do on Earth. And I think that that's just a fascinating concept, that going to Mars and studying Mars can tell us something about how did life start on the Earth.
Yeah, very, very cool. I love these when we can dive in with stuff like this on space presentations. So thank you so much for that answer. All right, Miss Huey's class, they're joining us in Hamilton. Just demute that mic. In fact, all our teachers can demute their microphones. It'll make it easier when we go to Q&A. But Miss Huey, come on in. Go for it.
Hello. Thank you so much. I know my class is loving every minute of this. Yeah, they're pumped. So again, we had a ton of questions, but I picked one that I thought would be interesting, I guess. A few kids asked this question. So They're wondering what the difference is, I don't know, maybe in tangible terms, between gravity on Mars and Earth's gravity.
So Mars is smaller than the Earth, but it's made out of approximately the same materials. It's just a smaller. So I think that the gravity is about 1/3 that on Mars. So you I have a little cheat sheet over here. Let me just, yeah. So on Mars, you'd experience 2/3 less gravity than what you experience here on Earth.
Yeah. I love how nerdy it is that you have a gravity cheat sheet just to the side of your screen. That's amazing. I want to do a shout out to our groups in Maryland and Massachusetts joining us too. We got all the states. We're going to try and get every state and province by the end of this. Let's go to North Carolina right now. So Miss Thompson's class is joining us in Asheville. Come on in and go for it. Hi, Miss Thompson. Oh. Miss Thompson, can you hear me? Maybe? Kind of, sort of? Did type some questions in the chat too. I'll come back to you, Miss Thompson. She did share in chat. Let's see if we have one of the questions from there. How long does it take to make a rover, Sarah?
It takes a long time. It takes many years and thousands of people. This particular rover, we got the approval to start building or to start designing in 2013, 2014, somewhere in there. But we were able to reuse a lot of the engineering designs from Curiosity from our previous rover, and in some cases even some of the spare parts that were built for that rover. So what we have to do, what we do first is we say, here's the what is the science we want to do? What is the capability? Therefore, what are the capabilities that this rover needs to have? And we write all this down very carefully, and that's a field called systems engineering. And where you're writing requirements and you're thinking, okay, this system needs to do that. That means this system needs to do that. That means this system needs to do that. And it's a several years long effort just to kind of write everything down and to make test designs and be like, I have an idea about how we're going to make this drill work. Let's do some prototyping and do some testing in the lab. We had a very long set of test drills, and we brought rocks in from all over Southern California.
Yeah.
And then you build hardware, and then you sort of beat it up in tests to make sure it's going to last long enough. We had like lifetime testing.
Yeah.
You have to, is it going to survive launch? So you put it on a giant shake table. Is it going to survive going through space and getting to Mars? And so we put it in this giant chamber that we pump down to vacuum, and we adjust the temperatures in. It's this whole complicated thing. And then we finally build the real one. And there's some final testing that gets done on that. So it's this iterative test, build, test, build, test. Okay, here's the real thing. Let's build that and test that too. Process. And it takes many years.
Very, very cool. I'd encourage all our classes to check out how the Curiosity rover landed on Mars with a sky crane. It's something we've covered in a lot of programs in the past. One of the coolest things ever done in science and engineering, if I do say so. And yeah, fantastic to cover rover questions, guys. There's so many coming in on YouTube as well. Right now, what we're going to do is go to Granville, Maryland, for Miss Rahim's school. I think there are 9,000 kids that are tuning into the school, or some ridiculous number. So we're going to take a couple questions in a row from the school. So Miss Rahim's group, we'll do 2 questions from you guys for now, and hopefully take some more in a minute. But come on up and start us with one. Hi. Oh, tech difficulties, guys. So your audio is not coming through. We can see you, and your audio should be working, but it's not. This is half the fun of video calls. Something has to go wrong, otherwise it's no fun. So come try, for Mr. Heem's class, if you guys could type your questions in the chat bar, I'll try and come to you and see if we get the mic working in a minute, but I'll go to Ms. Goraski's class right now to fill in while we're waiting for that. You guys can share a couple questions. So Ms. Goraski's, welcome in again, guys. Hi.
Hi, we have Abigail.
Hi, Abigail.
Abigail's going to speak really clearly. What was the biggest accomplishment you have done? The biggest robot you have done and the biggest challenge you have done?
Those are really good questions and very tricky. So this Perseverance, this is the robot that's, I think, the most complicated that I've been involved with. The biggest, this is the first one that I've been a part of from the very beginning. The previous, most of the stuff that I talked to you about were spacecraft that they'd already been built and launched. All the other ones I've worked on had already been built and launched by the time I joined the team. The physically biggest spacecraft was Cassini. It was about the size of a school bus, but it was a lot simpler. It's older, and just like a much simpler computer to run than these rovers. I'm very proud of a lot of the work that I did on Perseverance, but also one of the, like, if there's a single moment that's been a personal career highlight for me, was actually the Curiosity landing, because I worked for both the Curiosity mission and also that high-rise camera I was telling you about. This is the camera that we turned and took a picture of Curiosity on the parachute as it was landing. And we're going to try doing that again with Perseverance. But I was on both teams. I was doing a lot of running around and making sure that all the commands, that all the right people were talking to each other, because it's a very complicated thing to make this picture work. So then I got to do the NASA press conference where we showed everybody the picture, and that was pretty exciting. And I was on extremely little sleep. And so that was quite amazing. A major challenge for me has been just jumping in and not overcoming that little voice in the back of your head that says, I'm not sure if I'm supposed to be in this room. Yep. And being like, no, I have my expertise. I am bringing something to the table. The things I have to say are things that these people need to hear. And not, sort of overcoming not standing in my own way when trying new things.
I'm really glad you mentioned that, and it's funny because we get the chance to highlight amazing people like you, people that have trained their whole career for this, that have spent decades building up the experience and expertise to do these amazing jobs. And imposter syndrome is something that affects everybody, we've discovered. I mean, from astronauts to planetary geologists, deep sea explorers, and more. So I think that's an important message for kids, is that not everyone who comes on this broadcast is going in with absolute confidence in everything they do every minute of every day.
Very much so.
Yeah. But I love your story. And so I'm going to go to Mr. Huygens' class in a second. I think they got their tech working, which is awesome. What does that feel like? So you've spent years committed to this project, and there's this, quote unquote, like few minutes of terror where you lose communication and find out that it's landed on another planet. Something that you worked on has landed on another world. How does that feel? Like, walk us through that, because that's such a cool experience. No pressure.
No pressure. The 7 minutes of terror thing, like, if you guys haven't gone and seen that video, please do. And that's how we're landing again, only more so. We've got some new technology on our landing system to make it even more pinpoint accurate. And that's terrifying, because you've put all this effort into something, and now you find out if you're going to be able to wake up tomorrow and continue working on it, or if all of that was wiped away. Yeah. And then when it works, we were just so giddy and excited. And Curiosity landed at like 10:30 at night, local Pasadena time. And then we had to start shift, and we had, a 12-hour shift of looking at and figuring out what to do next, and sending up the commands to sort of unpack the rover and get everything started. And we were standing and looking at the pictures that had immediately come down, and I was standing next to another member of the science team, and And she just suddenly started giggling. And this was at like 1 a.m. And I'm like, Michelle, what's up? And she's like, it's not a test. It's the real thing. So we were all kind of in this like giddy disbelief that it worked, that we were really there, like all this effort. And suddenly you're like, it's here. And you're like, really? Oh my God.
What a great story. I do encourage you guys can watch the video of the 7 minutes of terror from the Curiosity landing. Again, Perseverance, you'll see this live on TV in just a few weeks, which is really, really exciting. So I'm glad we got a chance to highlight that. Ms. Rahim's class, we're going to try some questions with you guys, and I have them in chat if need be, but let's see. Audio working.
Hi.
Hi, it works. Yes.
So my question is if you're looking for water, why don't you just land at one of the ice deposits on like one of the
Question.
That is a great question. So it is challenging to land on Mars at all. And because Mars has very thin atmosphere, so we don't get to, our parachutes have to be super huge to slow us down and stop us from crashing on the surface. So we have landed in the Arctic, like I was mentioning with Phoenix, and there we dug down just like an inch or so and uncovered water ice. We tried to land on the ice at the south with Mars Polar Lander, and it crashed. It didn't survive, and we think that probably as it's landing, it's sending radar pulses to try and to understand how far from the surface it is, and there may have been some sort of confusion with the radar, maybe past some of it going through the ice and bouncing off of a layer of rock underneath and confusing it, and it didn't send out the landing gear in time and just went. We think, we're not exactly sure. In the case of this rover, because what we're looking for is we want not just water, so not just water ice, but we're talking about favorable conditions for life. Water is just the first step for thinking about life as we know it. So we need to find a place that has favorable conditions. That means liquid water. And it also means, liquid water for a long enough period of time, the right kind of chemistry that we can see remnants of in the rocks to tell us that this was a hospitable environment, a habitable environment. So we think that, so while today, everywhere you look, including in the ice, there's life. But when life started, we need something, some sort of nice, cozy place for it. And so that's why we're going to this crater that it looks like billions of years ago in the time frame that we think that Mars was habitable. This place is a particularly nice one.
Very, very cool. I love that question from our student. You could be on like a Senate budgetary committee in the future with questions like that. Why go there?
Why go there?
Right? I'm going to go back to Ms. Rahim's class for one more question. Time's flying while we're having fun, guys. We're going to take one more question. I'm going to share a few resources to keep the learning going. And unfortunately, we'll have to wrap up from there. But Ms. Rahim's students, come on back in and go for it. Come on, guys.
How do you guys plan on collecting the samples from Perseverance?
That was one of those major engineering challenges that we had to spend several years working on to solve. So we have at the end of, so there's the arm on Perseverance, and it's about, I think, 6 feet long. And it's got this giant box, the turret at the end. And this whole turret is like the size of one of our previous rovers, Spirit and Opportunity. So we basically have this huge box at the end of the arm, and it contains a couple science instruments and then also a drill. Inside the belly of the rover, we're carrying tubes. So what's going to happen is when we say, okay, that rock, we want to drill that rock, the arm is going to come park at the belly of the rover, and a little helper arm inside the rover is going to grab a tube and a drill bit and stick that onto the arm, which will then go and drill and collect the sample. The tube is in the bit, and so as it's drilling, the rock is going into the tube. Then the arm docks back with the rover, and the little helper arm grabs that tube and puts a lid on it, and then we carry that with us until we hit a place, we find a place where we're like, okay, this is a nice spot, it's kind of flat, it looks like it's very stable and quiet, and then we can put all of the sample tubes down on the surface. The current plan is that in the future, sometime, we will have a very simple rover that the Fetch rover will land on Mars and go pick up these tubes and put them in a box, and then drive that box back to where we have the Mars Ascent Vehicle, which is a little rocket, and put the box on the rocket, and the rocket will shoot the box up. It'll launch the box up into orbit around Mars. Another spacecraft will come and scoop up that box and fly back to Earth and drop it off. So it's a long campaign, a many-step campaign that we're working on internationally. We're working with the European Space Agency on to bring these samples back.
Very, very cool. And great question, guys. Again, I wish we could go for hours here. We've had easily 100 questions on YouTube, and I'm sure all our live classes would jump at the chance to ask more. But unfortunately, we're nearly at the end of the broadcast. So what I want to do is make sure the kids know where they can go to learn more about the NASA Perseverance Rover mission, about JPL in general, and about all the cool work you're doing. So with that in mind, if you go to the link below, that leads to the Perseverance Rover website. You can learn all about what's going on. Check out the landing. It's going to be on major networks all across the US and Canada, so I'd encourage you to tune in for that. It's going to be very, very cool. The Jet Propulsion Laboratory, again, one of the elite research facilities in the world. They have so many amazing education resources. So any of your questions probably have been answered there in some form or another. So check that out. And I know this is an unwieldy URL, but if you want to learn more about Sarah, below there's a little bit of a cool Q&A with her, more links and resources that she shared, which are really, really fantastic. So I'd encourage you all to check that out. Finally, Sarah, I have to link to this because it's happening in just a couple weeks for us. If you guys are like crazy about Sarah and amazing scientists in, scientists, explorers around the globe, we have our first ever Women Blaze Trails Fest in a couple of weeks. We're doing 50 programs in 3 days featuring incredible scientists and explorers from across the globe. Hopefully you guys get a chance to tune in February 12th through 14th. And I think you'll agree, Sarah, if people watch The Martian, it's just a great movie to inspire you to be an engineer. I was past the point where I could make a career choice like that, but if you were young and you watched The Martian, I think you're like pretty keen on duct tape from now on and things you can do in space. Right?
Absolutely. Absolutely. I should also mention, if you're interested in just following me, I am on Twitter at Milkysa, MILKYSA, and you can find me. There we go. You can find me there, and I'll take some time. I won't be able to answer everybody's question, but I'm happy to. I'm happy to chat when I have a little break.
600 DMs coming your way right before you're ending the mission. Good luck. Thank you so much for joining us today. I really, really appreciate it. Keep up the amazing work, and I'm so excited to watch Perseverance land. I wish it the best, and I'm excited to see what sort of amazing things it's going to discover in the years to come. Awesome.
Thank you so much.
Now, what we do at the end of every broadcast, Sarah, is I'm going to bring in all our live groups. So Miss L, Miss Shuey, Shannon, Miss Rahim, and Miss Goraski, if you want to join me in saying a big thank you to Sarah for joining us today as we wrap up. Thank you guys so much. Have a wonderful rest